Hey, we have here today another integral from the UNSW Integration Bee 2022. This was knockout round 3, problem 1. We have the integral from 0 to infinity of dx over x plus 1 over x squared. Okay, so you may notice this is a video that I just did on the other channel, just with a different method. And what I can do is post a link in the description to that other video so you can check that out. I think this way it's going to be a little quicker and a little easier. Not sure, you can let me know in the comments, but I think this way it's going to work out pretty nice. So now to get started with this problem, just noticing that we're going to have a squared term and we have these bounds from 0 to infinity. I want to make a u substitution, and for my u, what we'll do is we'll call our u equal to 1 over x, and then solving for x, we're just going to have 1 over u. I'll take my derivative and we get dx equals minus 1 over u squared du. And now I'll just go and make our substitutions. So when our x value here is going to infinity, our u is going to be just 0. And when our x value is 0, this u value is going to infinity. Now for the dx value, let's just write this like we'll put our minus sign in front of the du, and I'm going to write my u squared in the denominator, so I'm going to want to multiply this in. And then for within the parentheses, we're just going to want the reciprocal of each. So this is going to look kind of the same. If I just switch the order, we're going to end up with u plus 1 over u squared. And then I could take this minus out front of the integral and use it to swap my bounds. So then we'll get this back to where it was. This will become just, now we're going to be back to 0 to infinity. And then here, since what's in the parentheses is squared and our u is squared, I can just multiply the u inside the parentheses. So when I do that, we're going to end up with just u squared, and then u times 1 over u is going to be just a plus 1 here. This is going to be squared, and we have du in the numerator. But then because this is a definite integral, I can change the variable. So what I'm going to do is I want to change this back to x, because what I'm trying to do is add it to the original integral. So for this, let's just change the variable back to x. Okay, now I mentioned I want to add this integral to this integral, and we've got the same variable now, we've got the same bounds. The trouble is we don't have the same denominator, right? Here our denominator is x plus 1 over x, and here we have x squared plus 1. Well, I can fix that pretty easily. What I can do is just here, if I multiply by x squared in the numerator and denominator, and then if we multiply this x squared in here and here, let's see what we have. So when we rewrite this, we're just going to have x squared dx in the numerator, and then multiplying this is going to be the same thing as when we multiplied it in here. So we're going to end up with just x squared plus 1 squared. And then just to make it clear, this is our original integral we'll call I. We worked it down to here, and we'll call this one I, and this is still I over here. Now we want to add this copy and this copy together, and we'll have 2i. So let's see what that's going to look like. Now we had the 1 in the numerator here, so we added these together and got x squared plus 1 in the numerator in our 2 copies of the integral 2i. But then from here we get nice cancellation, so this is going to cancel here with one of these, and then we're just left with dx over x squared plus 1. But this is going to be nice because this is actually just arctan, so when we integrate dx over x squared plus 1, I'll just have arctan of x, and we're just evaluating this from 0 to infinity. Well, arctan at infinity, that's just going to be pi over 2. Arctan at 0 is going to be 0. But then this is 2 copies of the integral, right? So we need to divide off 2. So we'll divide off 2 here, divide off 2 here. And so for our final solution, we're just going to have pi over 4. Okay, not too bad. So we'll stop right there. Thanks everyone for watching today. Have a great day.